I cannot say 1 over here because that's the main thing. I am assuming both 1 and 2, then I have to prove both it n belongs to D and is true, no? So there is no 1. But anyway, that application also should be done. I don't know that I will be able to. I wanted to finish it today. Suppose it is not the case that again I am writing that. It is not the case that, sorry, n belongs to n. Pn. Suppose it is not the case that for each n belongs to n plus Pn is true. Thus, what will happen? Thus, there exists K belongs to Z plus such that Pk is false. And that Pk is false. Clearly, there exists n belongs to n. Clearly, there exists capital N belongs to Z plus such that 2 to the capital N is strictly greater than K. So far correct? No? I am assuming 1 and 2 because I have said assume that. So then I am supposing that this line is incorrect. So there is some K belongs to Z plus such that Pk is false. This one is a trivial thing. Clearly there exists capital N belongs to Z plus such that 2 to the n greater than K. Again, go to the same thing. Let capital N be the set of all n belongs to Z plus such that n less than simple n less than 2 to the n, this is capital N, and Pn is false. So far no question, no, because I just wrote the negation of the But clearly K belongs to F, no? Right? Why? K less than 2 to the n, K is an integer and Pk is false. Clearly K belongs to F. Therefore F is non-empty. Right? F is therefore F is non-empty. Clearly capital F is bounded above. Right? Because capital F is bounded by 2 to the n is bounded above. 1 by 2 to the n. Clearly capital F is a bounded above subset of Z plus capital F is the subset of Z plus, and it is non-empty, and it is bounded above. So it has a maximum. I will use it, prove it later. Just now we can assume that it has a maximum and it's no big deal. Thus, capital F has a maximum. As soon as this is done, I will prove maximum. Let M be the maximum of M be the maximum of capital A. All these space. You can see the board, no?
Yeah.
But to me it's not right enough. M be the thus maximum is always maximum is a member of the set, element of the set. Supremum or infimum doesn't have to be. Thus capital F has a maximum. Let M be the maximum of F. Thus, M is strictly less than 2 to the n, no? M less than 2 to the n. If M is a member of capital F, Pm is false. Right? Pm is false. I will write there. Because M is the maximum, therefore M plus 1 does not belong into F. Because M plus 1 does not belong into F. It follows that follows that what? M plus 1 does not belong into F. M is the member of the set. M is the maximum. Therefore, M plus 9 to the n and Pm is false. However, M plus 1 does not belong into F. Then what can I say? What can I say? I'm asking you. Very simple. M plus 1 does not belong into F.
M plus 1 can be the maximum. Cannot be the maximum.
Puta, M is the maximum, no? M plus 1 does not belong into F. It will never be the maximum because it's not a member of F. If something belongs to F, it is an integer and n less than 2 to the n and Pn is false. If M plus 1 does not belong into F,
it is either M plus 1 is greater than 2 to the n or M plus 1 is false. So that's true.
That was that. M plus 1. I can see my F. Yeah. M plus 1 is true, no? Right? Somehow I get tired when it is not bright enough. P plus 1 is true. That doesn't be with the case 1. Suppose that m plus 1 greater than or equal to 2 to the n. However, we know that m less than 2 to the n. Because m is strictly less than 2 to the n, we have that m plus 1 less than or equal to 2 to the n. Now m plus 1 greater than or equal to 2 to the n, less than or equal to 2 to the n, thus m plus 1 is equal to 2 to the n. However, this equation is true for 2 to the n, p 2 to the n. No? From 1 p 2 to the n is true. Hence, p m plus 1 is true. Other case 2, case 1 I got this, case 2 got that. Suppose p m plus 1 is true, no? Anyway, from either case you get p m plus 1 is true. Thus from either case p m plus 1 is true. However, from here, if p m plus 1 is true, then p m is true. Hence, from 2, p m is a very good pen, Buddha. P m is true. However, this is a contradiction. Because p m is a member of set, p m is false. This contradiction establishes A-S-T-A-B-L-I-S-H-E-S. Spelling correct, no? Establishes the theorem. That is the theorem. See whether you have any questions.
So can we also prove this by the well-ordered principle?
Well-ordered in principle, I don't know actually. I somehow, maybe all these are connected, so maybe there is a way to do it. I haven't thought about it. So I have used here that if bounded above, every bounded above subset of Z plus has a maximum. Of course it is true. But let's write a proof of that also to finish it. So anyway, then I have proved the backward induction. But you have to prove someday backward induction and forward induction are
Same thing.
Same, they are equivalent. And we are not going to be experts in induction here, but we are doing what is necessary to proceed in our course. Of course, other things are also very good if you can do so. So let's prove this thing because it is a nice application. Prove that for each n belongs to Z plus for each n belongs to Z plus each non-empty subset of 1, 2 bingo up to n as a maximum. Actually, no need to do this thing, but I am just doing it. People would know that as a maximum he has proved that kind of thing. But this proof is no need to prove, but still let's prove. Because somebody can argue these inductions, no need to prove, no? Because P1 is true. For each n belongs to any Pn is true, then Pn plus 1, no? Because P1 is true, P2 is true. Because P2 is true, P3 is true. Like that one can argue. Yeah, but anyway, proof. So this will be proved by induction. I say that this result looks trivial. Anyway, let us prove it by induction. Let Pn be the statement. This is a beautiful proof somehow. Let Pn be the statement. I wanted to finish this thing and start the analysis side today, but won't be able to do it because I had to do another example or what to do. Let Pn be this statement. Every non-empty subset of 1, 2, bingo up to n has a maximum. Let Pn be this case. Every non-empty subset of 1 to n has a maximum. So first we have to prove P1. So I am saying let capital A be a non-empty subset of singleton 1. If A is a non-empty subset of singleton 1, A must be 1. Thus, A is equal to singleton 1. Clearly, 1 is the maximum of the maximum of singleton 1, thus P1 is true. So P1 is true, right? Now suppose n belongs to Z plus is such that now suppose such that Pn is true. Right? Now I have to prove Pn plus 1. Let capital A be a non-empty subset of one 2 bingo bingo n plus 1. Clearly, n plus 1 belongs to A, O n plus 1 does not belong to A. Case 1, suppose we assume same meaning, n plus 1 belongs to A. Capital A is non-empty subset of 1, 2, all the way up to n plus 1, and I am assuming n plus 1 belongs to A. Therefore, n plus 1 must be the maximum. It is clear that n plus 1 is the maximum. Thus, in case 1, this is a very good pen put up. From where did you find this?
Below class.
Thus, in case 1, Pn plus 1 is true. In case 1, it is true. Now, case 2. Now, assume n plus 1 does not belong into A. N plus 1 does not belong into A. Now, capital A is a non-empty subset of 1, 2, all the way up to n plus 1. I am saying n plus 1 is not in the A, therefore, capital A is subset of 1, 2 up to n. However, we have suppose that Pn is true. No? By induction hypothesis, A has a maximum. Therefore, in case 2, thus, in case 2, Pn plus 1 is true. Hence, in either case, P1 plus is true. So I have proved that P1 is true. I have assumed that Pn is true. I have proved that Pn plus 1 is true. Thus, by induction, when I say induction, I mean induction. But am I right? Thus, by induction, Pn is true for each and belongs to it. That means each non-empty subset of 1, 2 up to n. This completes the proof. I will write it here in blue somewhere here. This line must go over there. I like this proof because it's not difficult but it's very nice. Writing proofs I enjoy. That's why I say you also need to learn to write. Then you will enjoy it. I mean, this is terribly simple, but it happens in a very nice way. So anyway, we have proved that principle of backward deduction. Intuitively, we can see that it is correct, but without the proof, you cannot take anything for granted in mathematics. That's what we say. So now we have proved it. So I want to prove at least one example from this. It takes time, but let's see, because I want to finish with it. That can do. Then I was planning to do sequences, but only 2 days for the sequences. So many things now, because this kind of thing also very important, because there are sometimes you have to write proofs with no epsilon in analysis also. So by writing this kind of proof, writing this kind of proof is a good motivation for that. So can you see, you asked me very good question, I told you, and we have something else. You can write 3 to the end also, proof remains the same. So, but we usually write 2 to the end. Can I guess? This time, before erasing, I asked. My wife says, you ask the question, right away you reply. I have nothing to do. Especially when there is something I like to eat, I answer, you don't want this, no? Enjoy writing, need proofs. That will make you a mathematician easy. Okay, now this is an example actually. This AMGM inequality, prove that. I want to show you an example, and of course there are some other examples. We are not going to do it now because we have time to be experts in induction. We should get to analysis. Prove that for each n belongs to n. A say plus for all positive numbers x1, x2 up to xn. This x1 plus x2 plus and so on plus xn divided by n greater than or equal to nth root of x1, x2 up to xn. We are going to write a complete proof. Proof. I say let us prove this by principle of backwards. That boy who just come for lunch just never come anymore, no?
I don't look like that.
Yeah, we should not tell him about the next lunch. If we inform him, he will be there. I know he is a guy like that. Let us do this by principle of backwards induction. Though I write this way, actual proof I can write only by backwards induction. Other thing I can just argue. But writing a proof, this is the only way I know. Okay, so let me end the statement. The statement for all positive integers, not real numbers, for all positive numbers x1, x2 up to xn, x1 plus x2 plus and so on plus xn divided by n greater than or sorry equal to nth root of x1 up to xn. Let Pn be this type. Okay. First, if we are going to use the backward reduction, we have to first prove P2 to the n is true for all n. Then we have to prove for all n if Pn plus 1 is true, then Pn is true. Right? So I say first let us show that P2 to the n is true for each n belongs to say plus, which is what we want to prove first. Let us prove this by prove this by forward induction. And you see in application, backward induction uses forward induction. Half of the thing done by forward induction. Okay, so let us prove this by forward induction. Let 2 to the 1 no, first, then we have to prove it 2 to the 1. No? Let x1, x2 be positive numbers. Then square root of x1, you know this one very well, minus 2 square greater than or equal to 0. Thus, x1 minus x2, no plus x2, minus 2 square root of x1, x2, greater than or equal to 0. Hence, x1 plus x2 divided by 2, greater than or equal to square root of x1, x2. Thus, we do the P of 2 to the 1 is true. Right? Now we have to assume that P 2 to the n is true and then show that now let n belongs to Z plus. Suppose that P2 to the n is true. Now we will prove P2 to the n plus 1 is true. Now let x1, x2, x2 to the n plus 1. Now let me positive numbers. Right? Consider the two positive numbers. One is x1 plus x2 plus and so on plus x2 to the n divided by 2 to the n plus x2 to the n plus 1 plus x 2 to the n plus 2 bingo plus x 2 to the n plus 1. I have taken two numbers. there are 2 to the n positive numbers here. Also there are 2 to the n positive numbers here. Same. Because P 2 to the 1 is true, we have that what? X1 plus X2 plus dingo plus X2 to the n divided by 2 to the n plus X2 to the n plus 1 plus X2 to the n plus 2 plus dingo X2 to the n plus 2 to the n if you want, divided by 2 to the n. One half of this. This is my first number, this is my second number, A plus B divided by.
So you should change the second number up there.
Same thing, no? 2 to the n plus 1 and 2 n plus 2 to the n both are same. Huh? 2 to the n plus 2 to the n is equal to twice 2 to the n. 2 to the n plus 1.
No, I mean the denominator there's no 2 to the on the second.
Ah! Thank you. So this number plus this number divided by 2 greater than or equal to square root of this guy times that guy. Square root of x1 plus x2 plus bingo x2 to the n divided by 2 to the n, this one times bingo x 2 to the n x 2 to the n plus 1 plus x 2 to the n plus 2 bingo plus x to the x subscript 2 to the n plus 2 to the n divided by 2. Right? However, we have assumed p 2 to the n is true, therefore I can write, I will write this way. This thing greater than or equal to nth root of x1, x2, bingo, x2 to the n. This part. Other part also not that, not n, 2 to n. Here also you get 2 to the n root of x 2 to the n plus 1 x 2 to the n plus 2 bingo x 2 to the n plus 2 to the n. Right? Because both of them are 2 to the n roots.
There's an extra square root mark.
Huh?
There's an extra square root mark no on the last line.
This one is not needed. So this one is equal to square root of 2 nth root of x1, x2, x2 to the n. This is silly guy. x2 to the n, x2 to the n plus 1 equal x 2 to the n plus 2 to the n. No? So this is equal to this is actually this whole thing, that part, if I say that is 1, y to the 1 over 2 to the n, no? Then I have to take 1 over 2 power. Therefore 1 over 2 to the n plus 1 root, no? Two to the n plus 1 root, first root of x1, x2 up to all the way x to the 2n. X to 9. Somebody can kill me. I say x to the 2n. X subscript 2n plus 2n. So, just write this way to see it better this way. So, I have wrote thus, where am I? I begin. Thus, 2n, oh sorry, x1 plus x2 plus and so on plus x to the 2n plus 1 divided by 2n plus 1 greater than or equal to 2n plus 1 root of x1, x2 up to x 2n plus 1. Right? Therefore, bn plus 1 is true. Therefore, bn plus 1, not n plus 1, b 2 to the n plus 1. First I wrote b to the 2 to the 1 is true. Assume that p to the 2n is true. Now we have this thing, that's by induction. What is n belongs to n? p 2 to the n is true. Right? So first part is induction, first part is done. Now I have to prove if Pn plus 1 is true, then Pn is true. So this is the Roman 1 of backwards induction. Now let us prove the assumption 2. Of backwards induction. Let n belongs here. Oh, over this I will create. Let n belongs to plus. Suppose that Pn plus 1 is true. I want to show that Pn is true. Then for all positive numbers, x1, x2 and so on up xn and xn plus 1. Come. x1 plus x2 bingo plus xn plus 1 divided by n plus 1 greater than or equal to n plus 1 root of x1, x2 bingo xn plus 1. Right? That is the meaning of Pn plus 1 is true, right? Now I am going to choose particular n plus 1 numbers. Now let I want to prove Pn, no? So I have to choose now let x1, x2, bingo, xn be positive numbers. I want to prove x1 plus and so on by plus and so on plus xn divided by n greater than or equal to n root of x1 up to xn. Now consider the and going fast, good. Now consider the n plus 1 positive numbers x1, x2, bingo, xn, comma, nth root of last one, x1, x2, bingo, xn. These are my n plus 1 positive numbers. Then I get x1 plus x2 plus and so on plus xn plus nth root of x1, x2 up to xn divided by n plus 1 greater than or equal to n plus 1 first root of x1, x2, bingo, xn times nth root of up to this, right? So if you n plus 1, right? Therefore, x1 plus x2 plus and so on plus xn plus nth root of x1, x2 up to xn greater than or equals to n plus 1 times you get here x1, x2. What do I write? Because this is too low, but I decided to do it because we are going to use it a lot. AMGM inequality. Without proving, I didn't use it. N plus 1 times you have, say if this one is y times, then y to the 1 over n, no? So it is like y to the n plus 1 over n, no? Right? So you can write it as y to the n plus y to the nth root of this one n plus 1. Anyway, you can write, no? Y to the n plus 1 is nth root of y raised to the power n plus 1. So, using that, n plus 1 times n plus 1 root of nth root of x1, x2 up to xn, this whole thing raised to the power n plus 1. Now, you can say then, you get x1 plus n's, x2 plus and so on plus xn, 3 dots plus nth root of x1, x2 to xn greater than or equal to n plus 1. Here n plus 1 power, here nth root, they cancel. N plus 1 times nth root of x1, x2, bingo xn. So then you get hence plus, so some other word, x1 plus x2 plus and so on plus xn. Here one nth root you can cancel, then you get n times nth root of 2xn. So x1 plus x2 plus xn divided by n greater than or equal to nth root of xn. Anyway, we use this inequality quite a lot. That's why I wrote it. So now I have wrote backward induction. This is an application of backward induction, and this is the only way you can write a complete proof of this thing. To me, actually, I don't know any other way. I cannot. You know, it is like after proving p2 to the 4, the similar method can be used to prove 15, 14, you know, backwards I can come, but this is a complete proof. Clear, no? No. So, now, basic things are the things you know over. I guess there are some 1 or 2 examples I should do, but not today. Later someday it will be done. Now we are going to go to the analysis. So anyway, I want you to know now, you can prove, you know the principle of mathematical induction. It has normal induction, strong induction, and backward induction. And you need to know that though I have proved, they are equivalent. And someday, someday, it is, if you know how to do it, is good for you. But someday I will come to it, because I have done what is necessary to continue this. Because you are using ANDM inequality a lot. And you get this thing, we will get Holder's inequality, Minkowski's inequality, like the Jensen's inequality, quite a lot of inequalities in analysis. So this is the easiest one, AMDM inequality. So they are interesting. And now I get tired by writing. Tired of writing. So this book is about, I asked you to buy this thing from them.
The analysis one?
Yeah.
Yeah, still didn't buy it because
They didn't have it.
no, we didn't go there.
Anyway, buy it, sequences and series both. That's is because I have written in a very, I have written this thing for students not like you, those who cannot understand anything. So I have written explicitly everything. So it is very easy for them to understand. Then to you it will not be a big thing. So the first chapter here is about sequences. You know the meaning of a sequence. So first chapter, there is nothing to do. You have heard the word monotonic sequences? Strictly, no.
Increasing or decreasing.
So monotonic means increasing or decreasing. You know the meaning of an increasing sequence, no? What is it? Say, I want to say xn is an increasing sequence. What does it mean?
For each A belongs to xn.
For each, I have given a sequence xn. I say xn is increasing. What does it mean? When I say xn, my style. That is greater than less than, that's the sequence.
For each xn.
No. No. Increasing.
xn is less than or equal
Eh?
to xn is less than or equal to xn plus 1 for each n belongs to Sn plus.
Is it? So, take so much of time now.
Sir, I had a question. How are we saying that a number is below to a sequence?
Below.
We can say x belongs to a set of something.
Oh,
How can we say that x is inside of a sequence? It is.
I see. I don't
X is
understand.
of the sequence, yeah, like that. So,
We have half an hour.
so sequence, all the terms are in a set called as a set. Huh?
I get tired by reading the word actually. Somehow it is a good pen. You are a Buddhist.
Yeah.
You say, Adinadana Veramani Sikkapadan Samadhyami, and you go and bring
It is in the same building.
Okay, good argument, good argument. So you will go to heaven then, or reach Nibbana. Okay, so could you ask your question again about the sequence?
If we have a sequence like 1 to up to infinity,
Yeah, sequence is x1, x2 like this, no? You, sequence is an ordered list
yeah,
with no end.
let's say that sequence is x xn,
Yes, xn sequence.
and let's say x2 is 2.
x2 is equal to 2. Okay.
In a set, we can say that 2 belongs to that set.
What is the set?
Let's say that those.
x2 is equal to 2, you said. I wrote it. Then what is the next thing?
Yeah, I was wondering if we can use 2 belongs to xn, like something.
If you want, you can write this way. 2 belongs to set of all xn and belongs to xn plus. And 2 is some member of. Is that what you are asking?
Yeah, I thought we can just use like this.
You are wondering whether you can write this way?
Yeah.
No, sequence. This is not a set. This is a list. It's a list.
So if you want to use the element of sign, it has to be a set.
Exactly. You can, no, you can, this is a list, this is a set. So you can say 2 belongs or 2 doesn't belong, either one belongs or 2 doesn't belong, either way. For the sequence, no, you can say.
What about
But-
the order list?
Ordered,
Ordered list.
That is an ordered list.
Yeah.
I don't understand. Ordered.
I mean, we said
Sequence is an ordered, unending list of numbers. It has order x1. You cannot write x2 before x1. x1, then x2, x3. If x2 is equal to 2, you can say 2 belongs to xn or what did you say? Ordered set.
no.
Nothing like
It
that.
was, yeah. I
Anyway.
mean, we used those brackets and wrote ordered list before doing sequences.
Because he was asking, put it on, that if an is increasing, an is a sequence, then average of an also increasing. An is decreasing, average of n is also decreasing. Try to prove. If an converges to 5, average of n also converges to 5. That's what I asked you to prove, no? If an diverges to infinity, average of n also diverges to infinity. If an diverges to minus infinity, average also diverges to minus infinity. an is oscillating may or may not imply that average is oscillating. That is the only thing exception. So you should be able to prove them. I suppose some of them are in your homework. You can try. I can see here. And if you take a sequence which is monotonically increasing as well as monotonically decreasing, what can you say about the sequence?
It doesn't have a limit.
Hmm?
It does not have a limit.
I didn't
It does not have a limit.
It does have, but before that, what can you say about the sequence? N is monotonically increasing and monotonically decreasing both. Monotonically increasing means for each n, xn less than or equal to xn plus 1. Monotonically decreasing means for each n, xn is greater than or equal to xn plus 1.
Every term is equal.
Then,
Every element of the sequence is equal.
yeah, so it is a constant sequence. I don't know whether it is one of the problems. And let's see whether there are things we should do. You know, addition of xn plus, you know, to add sequences, no? You know, to multiply sequences. There are two multiplications because some multiplication is if you have xn times yn, you use this A level. Did you do the dot product
Yeah.
for vectors?
Yeah.
So this dot product type thing. Then in A level x1, x2, x3, dot y1, y2, y3 is x1, y1 plus x2, y2 plus x3, y3. So that kind of product. There is another product. Then the other product is called Cauchy product, Cauchy. Cauchy product is like this. Suppose you have a0 plus a1 x plus a2 x squared plus a3 plus and so on times b0 plus b1 x plus b2 x squared plus and so on. So when you multiply this thing, a0, b0, b1 x b, you silly guys, silly. b0 plus b1 x plus b2 x squared plus b3 x cubed. This is equal to a0 times b0. a0 b1 plus a1 b0 times x squared. Then a0 b2 a1 b1 plus a2 b0 x cubed. Like this. This is called Cauchy product.
That should be x and x squared, right?
Yes. Yeah. This kind of multiplication, that is called Cauchy product. I suppose you have a question in your homework set. This way you must be able to prove e to the x times e to the y is e to the x plus y. You say a to the x is 1 plus x squared over factorial 2 and so on. This is the normal product, scalar product actually this is called. Tiggunita A level, yes.
So that should be b2. a0 b2.
Yeah, you are right. A0 B2. So, for instance, over there, in the second term, coefficients add up to 1. First one, coefficients add up to 0. Second one, coefficients add up to 1. Third one, coefficients add up to 2. It is like that. So you need to learn that thing a little bit for series. We are in sequences, I just told you. Then you can do I guess I don't have to say anything about monotonically increasing, monotonically decreasing sequences. You know that. Then what about bounded sequences? What is the meaning of about xn is said to be bounded? How? Why? When?
Let's say it is bounded by m. There exists m such that
No, you said x is bounded by m, there exists m again.
okay, it is bounded by
xn is said to be bounded if
there exists m such that all the elements in the sequence, or mod of all the elements in sequence is less than or equal to m.
But correct, what you are saying is correct, but go around a lot. Xn is said to be bounded if there exists a m actually greater than or equal to 0, such that for each n belongs to n, mod of xn less than or equal to m. Get used to that language. Then bounded sequences, you know, I guess. Then bounded above, you know the meaning. Bounded below, you know the meaning. Unbounded above, you know the meaning. Unbounded below, you know the meaning. Unbounded below means not bounded below. So, you know that. I don't have to spend any time with them. There are questions. Here, algebra. You know, addition of two bounded sequences is bounded. Product of two bounded sequences is bounded. Addition of two unbounded sequences addition of two unbounded sequences. Addition of two bounded sequences is bounded, no? If mod A less than or equal to capital M1, if mod B less than or equal to capital M2, then mod A n plus B n less than or equal to mod A n plus mod B n less than or equal to M1 plus M2. So addition of bounded sequences is bounded. Product of two bounded sequences is also bounded. Addition of two unbounded sequences, we can say. Why you are not happy with us? No, you can say, we can say. It cannot be said. The right way to say is, of course, even I say I can say, but the right answer is it cannot be said. Okay, then convergent sequences, that's important. So, for these things that I ask you questions, epsilon has nothing to do. Then convergent sequences is the place where analysis begins. You know the meaning of xn converges to L. What does it mean? The sequence xn converges to L if
For each epsilon greater than 0, there exists n such that mod of what's the sequence?
I'm sorry?
Sequence. Let's say
a sequence xn.
xn. So mod of xn minus epsilon is less than.
Mod of xn minus xn. Are you hungry? I am asking what is the meaning of xn converges to L. Xn is a sequence.
For each epsilon greater than 0,
Very good.
there exists n in
Z plus.
Z plus
Such that.
Mod of xm
Yes.
minus L
L.
less than or equal to epsilon for each n greater than m.
Okay, very good. It doesn't come that easily, it's still kind of.
It is easy to write.
Okay, anyway, you know, so you can prove some little equation converges to L, you know, I suppose you can prove. So let us prove at least one, because I have to make sure. Sometimes it is easy to say but difficult to do. Easy to say. Very easy one. What is this? Limit n tends to infinity. N squared plus 2 divided by n cube actually. 2n cube plus 7 is equal to how much? What is this limit?
1 half.
1 half. Very good. So proof is very easy, but let's do 1 without jumping, saying that it is very proof. So let me say epsilon greater than 0 be arbitrary, no? Right? Then we say notice that, oh, observe that, something like that we write, no? Notice that, observe that. Obviously, my R and B now you don't know about me. No difference. Observe that what? N cube plus 2 divided by 2n cube plus 7 minus 1 half is equal to 2 times 2n cube plus 7 divide 2n cube plus 4 minus 2n cube minus 7. This is equal to 4 minus 7 is minus 3 over 2 times 2n square plus 7. This is equal to 3 over 2 times 2n square plus 7. Look, right?
Cube.
Yeah?
2n cube.
Yeah, I guess I'm reducing step by step. So,
Easier to do the proof.
no, then it is easy to write the proof. So, I guess 3 over this thing. Now, what should I do? What did you, what, if you were solving, what would you do?
We need to show that that one is
I will simplify this thing and then ask you the same thing for n cube plus 14. Now what?
we need to do rough work to get some value to n such that this value is less than or equal to epsilon.
Yeah. Can you do it on the board or can you do it in your piece of paper?
Try.
Did you learn anything today? බලමුලා කරන දේවල්. කොහොම පණාර ගන්න එක නවත්තන්න තමයි මම මේක කරන්න ගන්නේ. මේක නිකම්ම බැලුවාම පේනවනේ ඕන්න මේක less than 3 වෙනුවට ඕන නම් 4 දාන්න පුළුවන් නේ. 4n cube දාන්න පුළුවන්. නේ? ඒ 3ට වැඩි එකක් ලියුවා මේකට වැඩි අඩු එකක් ලියුවා. දැන් 4 කපලා එක බෙදීම n cube ලියුවා. ඕන්න n cube කට වැඩි පුංචි එකක් මෙහෙම ලියන්න. දැන් ඒකට විශේෂ වැඩි කරදර වෙන්නේ නැහැ. ඉතින් මේ වගේ ඒවා කරන්න වෙනවා මේ හුඟක් ඉසිතෝ
Yeah.
Anyway, we need to do this sort of thing when you are, going to find that particular end node or whatever. So if you go this way, now this one less than epsilon, if and only if n greater than 1 over epsilon. So then we can write a let capital N be such that n greater than 1 over epsilon. By Archimedean property. Archimedean property. Then now let n greater than n, then n greater than 1 over epsilon plus 1 over n less than epsilon. Hence, this thing n cube plus 2 divided by 2 n cube plus 7 minus 1 half less than epsilon. So I have done that for each. But you did this correct, but sometimes if you are going to do this way, you cannot do it. You will find it. Here, luckily you had only 4n cube plus 14. Imagine you had 4n cube plus 16 n squared plus 18n plus 4, then you cannot do your method. Doesn't work here. That's right. That's the reason I decided to do things, because I knew that you would do it this way. If you are given a problem like this, you will be into trouble. Hence, for each n greater than n, that absolute anything n cube plus 2 divided by 2 n cube plus 7 minus 1 half less than epsilon. Thus, limit n tends to infinity. n cube plus 2 divided by 2 n cube plus 7 is equal to 1 half. So you need to be able to prove this sort of little things. They are not difficult at all, but you need to be able to prove. At the same time, it will be a good problem for you to show that limit of n cube plus 2 divided by 2 n cube plus 7 is not equal to 1/3. This way you are learning how to write, not very difficult things. Only to learn how to write. So you said that I couldn't do as much as I wanted to do today, but anyway, I finished introduction and stuff. Let Xn be a sequence and X be a real number, and let X belong to R. Then Xn converges to S if and only if for each epsilon greater than 0, the set of all n belongs to n. Such that xn minus x greater than or equal to epsilon is what? We know about sequences, because we are planning to finish everything about sequences by next Friday. I am saying let xn be a sequence and let x belong to R. Then xn converges to x if and only for each epsilon greater than 0. This set, what can you say about this set?
It does not converge. It does not converge to x.
This is a set.
Oh, so
what can you say about that set?
R minus x.
No. How can you say R minus X? This is a subset of positive integers. This set is a subset of positive integers. What can we say about the set? You given any epsilon, what do you know about the limit? That's why I told you, you need to think, because sometimes if you write without thinking, or from the notes on the board, or from the book by the prof, I mean, you may not be thinking. What should be this set? What can be said about this set? You know something, if xn converges to x, for each epsilon greater than 0, there is some integer, n, capital N, such that for each simple n greater than capital N, mod of xn minus x less than epsilon. So I am asking, what about the set of all xn minus x greater than or equal to epsilon? What can be said about that set? What are the things we can say about sets? We cannot say, that set is beautiful, oh this set is kind, this set is big. You cannot say that sort of words. So what are the properties of sets? The things we can say. For a human being, I can say for a girl, you can say, oh she is beautiful, she is gorgeous, she is tall, she is short, she is dead. I was going to say somehow, I swallowed it. But what are the things we can say about sets? If you take a sequence, you can say sequence converges. One thing, sequence diverges. Sequence is bounded. Sequence is bounded above. Unbounded. These are the things, words that we can use with sequences. What are the words we can use with sets?
Empty.
Empty, very good, one set. Other than that,
Infinite.
infinite, very good. Yeah, here you go. Words are coming now. Do you realize that still you are not thinking that much about, you are very good, but that lack of thought is sort of bothering you, troubling you. This set is, Putta, what can you say about this set?
It has an upper bound.
This set has an upper bound. Okay. What is the most important word about this set? This set is finite. Because after, if this is x, after some capital N, in this infinite set, this is an infinite set, over there mod of xn minus x less than epsilon. Before that, you will get the greater than or equal to epsilon. So it is finite, if and only if. This is where some people define the limit. This is how some people define the limit. So, next day when I come, I will ask, right, look, this is a very easy problem, but I want you to come with the solution, proof. I will not write it here. So we are starting sequences all the way up to lim sup, lim inf, etc. For bounded, unbounded, we have to finish all of it. As if you were in a, regular university, not in this course. This course you are learning like this, sequences. You are learning, but not enough.
Church of the
Then,
Church of the
yeah,